Hello, today we'll be going over the binary structure, binary trees. A binary tree is a hierarchical data structure in which each node has at most two children, generally referred to as left and right child. Each node contains three components: pointer to the left subtree, a pointer to the right subtree, and the data element. The topmost node in a tree is represented by the root. An empty tree is represented by a null pointer. This is because there is nothing in the tree. Here we can see a diagram showing that each node has at most two children. Next, we have the terminologies. First, we have the root, which is the topmost node in a tree. Parent: every node, excluding a root, in a tree is connected by a directed edge from exactly one other node. A child: a node directly connected to another node when moving away from the root. Leaf or external node: a node with no other children. An internal node: a node with at least one child. The depth of a node: number of edges from root to the node. Height of a node: the number of edges from the node to the deepest leaf. The height of the tree is the height of the root. In the binary tree to the side, we can see that the root node is A. The tree has 10 nodes with 5 internal nodes. Example: A, B, C, E, and G, and 5 external nodes: D, F, H, I, and J. The height of the tree is 3. B is the parent of D and E, while D and E are children of B. Now we have the advantages of trees. Trees are very useful and frequently used because they have some very serious advantages. Trees reflect structural relationships in the data. Trees are used to represent hierarchies. Trees provide an effective insertion and searching way. Trees are very flexible data, allowing to move subtrees around with minimum effort. Here we have types of binary trees, which are based on the structure or shape of the tree. First, we have the rooted binary tree. It has a root node, and every node has almost two children. Next, we have a full binary tree. It is a tree in which every node in the tree has at least 0 or 2 children. The number of nodes, n, in a full binary tree is at least n equal to 2h minus 1, and at most n equal to 2h plus 1 minus 1, where h is the height of the tree. The number of leaf nodes, L, in a full binary tree is the number, capital L, of the internal nodes plus 1. Example: lowercase l equals capital L plus 1. Next, we have the perfect binary tree. It is a binary tree in which all interior nodes have 2 children, and all leaves have the same depth or same level. In a perfect full binary tree, L is equal to 2h and n is equal to 2h plus 1 minus L, where n is the number of nodes, h is the height of the tree, and L is the number of leaf nodes. Next, we have the complete binary tree. It is a binary tree in which every level, except possibly the last, is completely filled, and all nodes are as far left as possible. The number of internal nodes in a complete binary tree of n nodes is floor n divided by 2. And now, the balanced binary tree. A binary tree is height balanced if it satisfies the following constraints. The left and right subtrees' heights differ by at most 1, and the left subtree is balanced, and the right subtree is balanced. An empty tree is height balanced. The height of a balanced binary tree is O log n, where n is the number of nodes. And finally, the degenerate tree. A degenerate tree is a tree in which each parent node has only one child. It behaves like a linked list. Now we've seen all of the shapes of binary trees. Moving on, we can now look at some examples.
So let's go ahead and program bnode as the small data structure I was discussing previously. So the very first thing we need to recognize is that bnode is a small data structure used for binary trees, very similar as we did with node in linked lists. If you remember, linked list owns a node containing the value and then .next. When we use double linked list, we use something .previous as well. So we're going to do something similar. We need to hold the value, but also we need to store a left reference to another B node and another reference to the right of B node. So basically we have those 3 fields. The only difference is that here the value, we're going to store integers just for the sake of demonstration and just for validation as well. And left and right, both of them are B nodes. So B nodes is the definition that we're creating right now. And here we have both declarations. The next thing that we need to do is to provide the constructor. As you remember, constructors are in charge of initializing all the fields in the class. So when we have a constructor like this one, so what we need to do here is to initialize this dot value will contain the value, will be initialized to the value provided as a parameter. Now, the left and right, they're fields. Indeed, we need to initialize them as well. So here what we can do, we can say that this dot left is the same as this dot right, which is the same as null, right? The only thing that we're doing here is we're initializing the left and the right to the null, both of them, because we only provide one parameter in this constructor. Now, since we need to initialize all the fields, that's why we must initialize them as well, at least with the default value. Now, I'm gonna exercise a feature that we have in object-oriented program, which is called method overloading. I want to exercise this method overloading, in particular, constructor overloading. And for that, we're gonna create another method called, another constructor, which seems like a method, that contains value, a no reference to the left, and a no reference to the right. Now, the purpose of the constructors, as I mentioned, is to initialize all the fields. So this value will contain the value. This left contains the left I'm providing as a constructor parameter, and this the right will contain the right as the constructor parameter. Okay, so interestingly, we have two constructors to provide flexibility to the computer user. Sometimes we have all this information. Sometimes the only thing that we have is the value, and we don't know how to connect it yet. So what I want to do in this point is that I want to use method overloading, or constructor overloading, by calling something called this. So this is a powerful keyword that identifies what is in this class. In this class, for example, I'm using Visual Studio at this point, which is suggesting that you can use this constructor. So basically says there is a constructor in this class that takes three values. In this case, the value is an integer, but also left and right. Since we don't have left and right, we can simply just providing the null for both of them. Since after all, that's what we're gonna do. I know it looks like a lot of elaboration for a simple task, but I just want to elaborate this more just for the sake of demonstration of this nice feature. I like it a lot, and I don't think I'm the only one. If you know how to explore and exploit this feature, you will actually get the juice of the entire object orientation programming, the whole objective. Later on, you will see more examples about this. Anyway, I just wanted to show you that part here. We're gonna come back to this class in a little bit, but let's create bnode tester. So the next thing is that we're gonna create a couple of objects, a couple of nodes, bnodes, that will allow us to create a shape like the following. So notice that here we can see a tree composed by 9 nodes. So they're all connected by the left and by the right. So the whole idea here in this tester is to create 9 nodes. I'm gonna declare them, and then after that, we're gonna connect them. So notice that each node only contains a value, right? And we're gonna implement that by using the very first constructor that we use in the bnode. So let's go ahead and declare them. Let me just start typing here. So we're gonna define and declare the bnode objects. There's some name, as you can see here, N1 and 2, they're denoted all the way to N9. So let's go ahead and do it. So here we create those 9 nodes with an integer. Again, let me just repeat again. We're using the very first constructor. Notice that at this point, only the value of the bnode contains the value of passing. This is the number 21, 11, 16, and so on. The rest, the left and the right, they're null. So now the next step is to establish the connectivity. The way we're gonna do this, notice that N1 is the root. We already know that. So here what we're gonna do, ladies and gentlemen, we're gonna say N1 has a left, and that it will be connected to N2, as you can see right there. Notice that we're just connecting the references to the nodes. In similar fashion, we have N1 dot right, we have a connection to N3. So notice that here, the only thing that we're doing is connecting. This is the connection that we're creating between left and right for each node. Let's continue working with the rest of the nodes. So we established all the connections between all the nodes that we can see here in this tree. Notice that N4 and N5, that left and that right, we didn't have to update anything from there because by default it's been already initialized into the null. Similar fashion was for N6 and N7. And notice that because the dot left from N6 and the dot right from N7, they're already null. So we don't have to do anything there. So let's go ahead and print the root. Now, we know what's going to happen at this point. This n1, as you can see, since n1 is the actual root, is a node. And we're trying to print here the 21, maybe something else. The only problem here, we already know that we don't have a toString, so this will print the hexadecimal address location. Check this out. As you can see, as you probably already know, it's going to print the hexadecimal address location for that particular object. So here we have B node that is located at that funky hexadecimal address location. This is fine. I mean, we don't have a toString, so we're going to go back to the entire B node in order to give this proper visualization or representation, text representation of the object. But before doing that, let's try to implement some kind of those transversal algorithms. And I want you to pay attention because this is where the beauty of recursion takes place. So notice right here that I create the method preorder. You probably remember that preorder is pre means root, left and right, yeah, and I'm providing a node as a parameter called capital R just to distinguish that this will be my root. Now in between, this is what's going to happen. I'm going to steal this system out print line that I got from the main. I'm going to put it here. And what we need to print is basically, remember the algorithm is root.value. And then we need to move to the root.left and then to the root.right. That is the algorithm. Of course, this will not compile because this is not a statement. What we need to understand is that here we need to call ourselves with the left. And this is what we were doing. You probably remember why I was making the big deal with hitting those nulls. And here is where we're going to see the reason why. So we're going to call this method call, this recursive method call, basically takes care of the left and the right every time we process the preorder. Now, this is the idea. This is not correct. We're going to call our method preorder from the main using the root, in this case, n1. So here we experimenting an issue, okay? So the issue is the following. It seems to be that we got 21, 11, 7, and boom, error. Notice that the tree that we have right here, here is the root, 21, and then the algorithm is going to the left, which indeed is 11, and that will be the root. So we print 11 after that, and then we move to the dot left, which is 7. Indeed, there's the root again. And then we go to the left, and the problem hits here, because once we go to the dot left, it's a null, as you can see here, but we're trying to get some access to that. That's where Java is throwing you something called null pointer exception. Every time we're trying to access a value from the null, it will point to an exception. Remember that the null is the default value for any object in Java. So we're trying to extract some information from the nothing. So that's not cool. So here, at least we were able to navigate through the left branch of this tree by accessing the dot value for every node. But when we arrive towards the end, we're trying to access that to the null, and that's why we got this null point exception. How do we fix this? Well, we need to condition the preorder. And by doing this, we can do this. If the root happens not to be the null, what we can do, we can print the value, move to the left. When you're done, move to the right. And when you're done, you basically return the access, return the control to whoever calls you. Check this out. As you can see, and you can trace this at home, we basically got all the values. We can use the power of recursion right now, as you can see, and very systematically, recursively, inductively, we can just go and access the preorder to the left, the preorder to the right. Every time just checking if we don't hit the null, because that's the base case. But if we do hit the base case, just a return and return the order, the control to whoever method call was done. It's a very amazing one. So we can do preorder. We can also do in order. How about that? And if you don't mind, I'm just going to use the power of the copy and paste just to do a couple of simplifications like the following. Okay, now that I encourage copy and paste, I just do this for simplicity purposes. So just you can visualize this. But the problem with copy and paste, you think you're done, but that's not true. Check this out. This if statement. Notice that we still have, even that I changed the name of our in order, the in order means that you need to process the root in between calls from the left and calls from the right. So here, what I'm going to do, I'm just going to print it in between, in the middle. I want you to pay attention to what's going to happen at this point. I'm going to call in order. and we got these results. So notice that in the tree that we're working at, we have a binary search tree, which I'm going to talk about that in a second. But notice that here, what we have, they're in order, they're in ascending order. I'm going to explain that in a second in the next piece of code, in the next presentation. But these are in order, not because the name is in order, it's because the configuration of the tree that we have it. Notice that to the left of every node, there's a smaller value. To the right, there's a greater number, just a larger number. So this is what we call a binary search tree. So a binary search tree, we have this ability to store values to the left, whatever is smaller than a current element, and to the right if it's larger than that value. So we're going to talk about that in the lesson. So I hope this kind of gives you a nice introduction about the coding, but I just want you to understand the declaration of the B nodes objects, the connectivity, and of course the invocation of this method.